What if parts of Earth's original body untouched by time, fire, and cosmic collision still exist beneath our feet? Long before the Moon was born, our planet may have held a very different chemical identity. In this video, we explore a groundbreaking discovery: ancient rocks from places like Greenland, Canada, Hawaii, and a union may carry the signature of Earth before it collided with Theia, the Mars-sized object that helped create the Moon and reshape our world forever. From rare isotopes to deep mantle mysteries, this journey reveals how science is peeling back the layers of planetary history to answer one haunting question: is the original Earth still here? Research has shown that certain regions, such as Union Island, host rocks with chemical composition similar to Earth's early state before the Moon formed. Scientists have discovered that rocks from Canada, Greenland, and Hawaii contain significantly less of the rare isotope potassium-40 compared to rocks from other parts of Earth. According to researchers, this suggests that these rocks are made of materials that existed on Earth before the massive impact that led to the Moon's formation. At the dawn of Earth's history, a Mars-sized object collided with the early Earth. This powerful impact ejected a large amount of material into space, material that eventually formed the Moon. After this event, Earth's surface remained molten and hot for a long time. According to recent studies, the impactor named Theia may have delivered a substantial portion of the water now found in Earth's oceans, helping make the planet habitable. As a result of this ancient collision, Earth's structure was so dramatically altered that today, about 90% of its composition is a mixture of early Earth and Theia. A small portion of other materials was later added to Earth's crust through meteorite impacts. However, Dr. Nicole Nye from MIT raised the question: could untouched remnants of early Earth still exist? To find out, she and her team aimed to identify features added to Earth by Theia and then search for samples that lack those features. By analyzing meteorites, the research team found that these objects are generally richer in potassium-40 than Earth, meaning the ratio of potassium-40 to other isotopes, potassium-39 and potassium-41, is higher. If this trend has remained stable over time, then Earth must have had significantly less potassium-40 before meteorites arrived. This is a striking result, considering potassium-40 makes up only about 0.1% of the total potassium in Earth's crust. Although it's possible that Theia was also poor in potassium-40, and the excess isotope was later delivered by meteorites, researchers considered this unlikely. Therefore, they concluded that if rocks are found with significantly low potassium-40, they likely originated from a time before Earth collided with Theia. Researchers identified two types of locations as the best candidates for finding such rocks. First, regions with Earth's oldest known rocks, such as Greenland and parts of Canada, and second, areas with younger rocks sourced from deep within Earth's mantle, places that may have escaped Theia's influence. Dr. Nye explained, if this potassium signature is preserved, we should look for it both in ancient rocks and in materials that have risen from Earth's depths. When researchers analyzed samples from ancient rocks in Greenland and Canada, as well as volcanic islands like Hawaii and Union, using a mass spectrometer, they found that these samples contained about 65 parts per million less potassium-40 than other regions. This low amount suggests that the composition of these rocks may be nearly pure early Earth material. Elements like ruthenium and molybdenum also show isotopic differences between Earth and meteorites, but due to their behavior during core formation, they can't be used to confirm these findings definitively. One major unanswered question is why early Earth was so depleted in potassium-40. Some meteorites also contain very little of this isotope, but none match the isotopic composition of the four regions studied. Nye and her colleagues acknowledge that they still don't know why Earth's potassium composition differs from other solar system bodies. Nye suggests that a broader set of meteorites should be studied, as one might match Earth's pre-Theia composition. It also remains unclear how these specific rocks avoided contamination from Theia's potassium-40.